Hello, everyone. My name is Junyao Yang from Michigan Technological University. Today, I'm presenting efficient modeling of random sampling-based LRU. This is joint work with Yucheng Wang and then my advisor, Zhengling Wang. So cache plays vital roles in storage hierarchy. Many modern systems rely on caching to achieve high throughput and low latency service. So the cache miss ratio, or conversely, the hit ratio, is one of the main metrics for measuring cache performance. Even slight improvement in cache hit ratio can lead to drastic end-to-end performance improvements. A miss ratio curve is a function relates cache size to cache miss ratios. Miss ratio curve is a very powerful tool for dynamic cache memory allocations. So for example, this is a miss ratio curve of a storage workload from Microsoft Research. In this particular instance, with A from miss ratio curve, one can make a small increase in cache size, and then it could lead to a drastic reduce in the cache miss ratio, which leads to a huge performance improvements. So before we proceed further to our work, let's briefly talk about the random sampling-based replacement. Random sampling-based replacement policy use random sampling for eviction, which decouples objects priority from ordering data structure. Many existing works, such as hyperbolic caching and LHDs, use such techniques to remove overhead from ordering data structure. In-memory cache like Redis implement both of its LRU and LFU based on random sampling mechanisms. So in this work, we particularly focus on the random sampling-based LRU policies. For simplicity, we call it K-LRU. In K-LRU cache, when evicting objects, the cache randomly selects K objects, then evicts the least recently used objects among K objects. So we observed that sampling size of K-LRU cache sometimes could have huge impacts on the miss ratio curve. So this figure here compares miss ratio curve with different sampling size from 1 to 32. We see that there exists a significant gap between miss ratio of different sampling size. Unfortunately, existing work on MRC construction are mainly focused on the LRU curve, which does not take sampling size into consideration. So the specific goal of this work was to efficiently construct accurate miss ratio curve for K-LRU cache with arbitrary sampling size K. So first, let's take a look at the history of MRC curve generation techniques. In the 70s, Mason proposed a generic stack algorithm which can construct miss ratio curve in just one pass. However, the time complexity of the original algorithm was too high for actual use. So more recent work like Sharps and AET reduced the time complexity down to big O of n with constant space overhead. But the problem is these algorithms are built for exact LRU policy. They did not take sampling size K into considerations, so it does not work well with the K-LRU cache. So next, we divide the remaining talk into 4 different sections. First, I will briefly describe the generic stack algorithm, then introduce our KRR algorithm, which is a probabilistic stack algorithm that will approximate K-LRU. And next, we adopt spatial sampling from Sharps to scale down our KRR stack. And then lastly, we show that our algorithm is practical for online KRU and miss ratio curve generation. So Mason's stack algorithm simulates miss ratio curve for replacement policies that satisfies inclusion property in just one pass. These replacement policies are also called stack algorithms. LRU, MRU, RFU, and OPT are all examples of a stack algorithm. So here we illustrate how basic stack algorithm works. On reference to an object on stack position 5, we move the object to stack top. Then we perform a linear scan through the stack and keep pushing the lowest priority object down the stack to position 5. This means that there is a linear time cost to update the stack for every reference. Then to obtain miss ratio curve, we collect stack distance while processing the reference string through stack algorithm. The stack distance is simply the distance from stack top to object's position. Once we obtain stack distance distribution of the workloads, miss ratio curve is simply a complementary cumulative distribution function of the stack distance distribution. So the main challenge we faced is that K-LRU is not a stack algorithm because apparently K-LRU does not satisfy its inclusion property. So to address this, we proposed a new replacement policy called KRR. So KRR is actually a stack algorithm, an algorithm that satisfies inclusion property. And then another interesting characteristic of KRR is that it approximates K-LRU well. Because of that, we can use KRR miss ratio curve to approximate K-LRU's miss ratio curve. So here I'd like to go through the similarity and difference between K-LRU and KRR. First, K-LRU and KRR are both probabilistic replacement policy, Both policies share the same eviction probability function. The subtle difference between them lies in their definition of their ranking functions. In K-LRU policies, objects are ranked based on recency. The ith object has ith recency ranking, where under KRR policy, objects are ranked based on its current stack positions. The ith object appears on the ith position of the stack. Here, I'll skip the detailed rationale of why KRR approximates KRU wall, so please see our paper for detail about these sections. So we talked about how basic stack algorithm works. To add on top of that, here we will describe how KRR stacks works. So just like the original stack algorithm, on reference to an object at stack position phi, we bring the object to stack top and perform a linear comparison on the way to position phi. And then for each comparisons, we perform a random draw. And then for each random draw, there's two possible outcomes. The object at stack position I is either going to stay at stack position I, or the object could be pushed down for further comparisons. So in case if the object is pushing it down for further comparison, we call these positions swap positions. So one interesting thing we found is that under KRR stack, the expected number of swap position is bound by log phi, where phi is the hit position or the reference positions. This implies that instead of naively compare every positions down the stack, alternatively, we can just perform one-way shift on these swap positions. So since there are only log phi of them, right, it could be potentially much faster than linearly scan through our position if we just perform a one-way shift just on these swap positions. So in order to do that, I want to ask the next question, which is how do we identify these swap position like in an efficient way? Our first attempt is very simple. So instead of perform randomized draw on every single stack positions, we ask whether they contain at least one swap position in an interval stack positions. If answer is yes, we recursively break it down in a larger interval into smaller sub-intervals until we identify our swap positions. Asymptotically, this approach only takes log phi square time, which is considerably faster than the original linear time per stack updates. So the previous top-down approach has complexity of log m squared, but we soon realized that the swap position can be also considered as the evicted object. So similarly, finding swap location or swap positions is equivalent to finding eviction candidates in the KRR cache. We then use the inverse cumulative distribution functions of eviction probability to compute the swap positions iteratively from the largest referenced position or hit position to the stack top. By doing so, it actually only requires big O of log phi time to find all swap positions, which is considerably faster than the linear time per update in the basic stack update methods. So again, please see our paper for detailed description of both methods for finding swap positions. So by using the backward stack update methods, we basically reduce the time complexity of KRR stack algorithm to big O of n log m instead of previously big O of n times m. And then the space complexity of the KRR is still proportional to number of distinct objects in the workloads. So to make KRR practical for online applications, we adopt a very effective sampling method, which is called spatially hashed sampling, which is proposed by Wasbergers. So here I'm going to illustrate how spatially hashed sampling works. So first, we have a reference L. The reference is first going through a hash filter. If it returns no, we simply skip the reference. If it is a yes, then the reference is going to KRR stack. The KRR stack returns the corresponding stack distance. And then lastly, we simply scale up the stack distance by the expected portion. So since the reference is spatially filtered, this essentially scaled down the original KRR stack, which significantly reduced the KRR stack's space overhead. So this method has been tested in several other works. It all shows that even under a very small sampling rate of 1/1000s or even tens of thousands, the scaled down version of the workload can still very accurately approximate its original workloads. So for our evaluation, we use well-known storage trace from Microsoft Research, and then some synthetic YCSB workloads. Also includes the recent key value cache traces from Twitter. And then for more detailed description of each workloads, please check our papers. So in our experiment, we found that there are two different types of trace. One is traces that are very sensitive to change in sampling size. And then there's also traces that are not sensitive to change in sampling size K. So here we show 6 representative traces that are relatively sensitive to change in sampling size. In this figure, we showed K-LRU mixed ratio curves with K ranging from 1 to 32. And then we also plotted exact LRU curve, which is colored in black. So again, prior LRU MRC construction techniques only approximates MRC for exact LRU curve. Therefore, use prior techniques cannot accurately capture those K-LRU curves accurately. So especially when K is small. So our techniques take sampling size K into consideration, which generates more accurate MRCs for different Ks. Additionally, by simulating multiple different K-LRU MRCs, the graph not only help you make better memory allocation decisions on cache, but also provides the optimal sampling size K for each workload. So there is also traces that are not sensitive to change in sampling size. So for these traces, their mixed ratio curves looks almost identical regardless of the sampling size. In these cases, our KRR stack can also generate a very accurate mixed ratio curve with almost negligible errors. So for accuracy, here we illustrate the accuracy of KRR stack using 2 example traces here. The dotted line here represents our approximation, and then the solid line is the actual mixed ratio curve with different colors corresponding to different sampling size. And then we also plotted the exact LRU curve to show the difference between K-LRU and the exact LRU. So as we can see here, our approximation is very close to the actual K-LRU mixed ratio curve. And then quantitatively, we also measured the average mean absolute error across all workloads. And then we show that for KRR stack alone, the mean absolute error is generally less than 0.001. And then for KRR with spatial sampling, the mean absolute error is slightly more, which is 0.003. So for time and space overhead here, so for time overhead, we compared the time overhead with shorts, which again is an LRU MRC approximation techniques based on spatial sampling. We evaluated using combined MSR trees, which has about 450 million requests in total. We show that our second backward stack update version performs very close to shorts. And then the first top-down approach has about twice the amount of time overhead. And then for more realistic scenarios, we also attached our KRR stack to actual Redis instance. And then we also observed that KRR only consumes very small fraction of in terms of both time and space. From space overhead, it's less than about like 1 megabytes of memories. So in conclusion, this work proposed a new probabilistic stack algorithm, KRR, which accurately approximates KRU MRC with arbitrary K in just one pass. And then our evaluation shows that KRR with spatial sampling are efficient enough for online KRU MRC generations.